We're ready to start. We are exploring today the transport layer. We started saying a few words about UDP. Today we'll continue and see how UDP is viewed by a programmer. So this is a C way of using UDP. In the lab you will use Python probably, which is very close. This is illustrating a client and a server. Those are toy programs. The client sends a message, a string of characters, to a server that displays it on the screen. So this is the simplest program you can think of. But still, for such a simple program, you need to do all those system calls. You need on both sides to call a socket. A socket is like a file descriptor. It is instructing the operating system to open a buffer for you and give you a number that you can use to read data from this buffer or send data into this buffer. Then you need to bind. On the server side, binding it means instructing the operating system of the service port, of the port number that will be used by clients when sending to this machine here. So if this server would be a DNS server, the port number would be 53. If this is your toy example, you give it another number, which is not a reserved number, a number that is not below 1024. On the client side, you can either choose to give a port number or not. If you give no port number in the bind, that means you let the operating system give to you the port number. If you choose a port number, you have to know what you're doing, because if another system is using the same port number, you may have conflicts. If you're doing two systems that are connected to the same or use the same port number, they will both receive the data that goes to this port number, for example. Even on the client side, if we think we send data to the server, but the server might respond to it in some more sophisticated cases, so we may receive here. And then once you've done that, in the simplest case, you use a call such as send to. The to in send to means that in the arguments of the call are the message, of course, but also the identity of whom you're sending to. What is this identity? It is the IP destination address and the port number of whom you're sending that to. On the server side, the dual of this is receive from. Receive from means if you call this receive from, you consume one message that has been received if one message has been received. If no message has been received, the default behavior in most systems is to block. The program that calls a receive from and there is no message to receive is blocked. The program stops until some message is delivered. And receive from means you will receive the message, but also the indication of the source, the IP address, and the port number of the source. They will be available here. So, of course, the program hopefully is doing something intelligent. For example, if this program is a DNS server, it will do its job of a DNS server, try to satisfy the request, and cache the from indication, the source IP address and port number, in order to know when providing a response to whom send the response. I said here when we do the send to and the receive from, we talk of IP addresses. So here you're exposed to whether the IP addresses are IPv4 or IPv6. So the low-level sockets that are shown here are dependent on whether it's IPv4 or IPv6. So you typically say that when you create the socket here. So this is an IPv4 socket, for example. In Python, there are higher-level constructions that allow you to create things that are independent, but the low-level are not independent. Very often, when people use UDP sockets, they use this thing called connected UDP socket that creates a lot of misunderstanding. So I'll say a few words about it. UDP is connectionless. The fundamental behavior of UDP is the one I have illustrated in the previous slide. When you're sending, you can send to anybody because you use a send to, and you can send on the same socket to anybody. You can send to different servers on the same socket. When you receive, the same thing. You can receive from different sources. That's what a DNS server does. A DNS server on the same socket that is used to do its job of a DNS server receives from any DNS client. You can change this behavior. For example, if you're using a Skype session that using UDP for a Skype session, for something that will last a long time, you can force a socket to be reserved for a source-destination pair. And this forcing is called connecting the socket. So if you say connect the socket on the client side, it means that you allow this socket to work only with a given remote system. So you give the IP address and the port number of the remote system. And from now on, this socket can only be used with that remote system. And the benefit is that you don't need to say whom you're sending to, you just send. So it's like writing into a pipe or writing into a file. But again, I insist that this is more caching local information. The UDP protocol itself doesn't have any state information. I mentioned UDP, IPv4, IPv6. I mentioned already there is no IPv4, there is no UDP v4 and UDP v6. There is IPv4 and IPv6. If you use low-level constructions, probably you have to say whether you use IPv4 or IPv6. So as I mentioned here, it's when you create the socket, you have to say, I use an IPv4 or an IPv6 socket. This is a bit old-fashioned, but this is what is done in most programs that exist today, and even in many programs that are still developed today. In Lab 3, we'll ask you to write an IPv4 program, but we'll ask you also to write a more modern program that is a program that is independent of whether we use IPv4 or IPv6. How can we be independent? If I talk to another machine, I need to know its address and also whether it supports IPv4 or IPv6. If I want to be independent, that means I have both. I am on a system that runs both IPv4 and IPv6, and I speak to another machine. How can I know whether I should use IPv4 or IPv6? Well, there are zillions of ways to do it, but the normal way is to go to DNS. So if I want to talk to another machine, I use its name, not its address, and I will go to DNS. There are many ways to do it. One is get host by name, or the more modern version, get address info. That's a system call that allows you to give a name, like www.epfl.ch, if you're using UDP to access it, with quick, for example. And it will return to you all the addresses that this system has, the IPv4 and the IPv6 addresses. If it has only an IPv4 address, then you know you have to use IPv4. If it has only IPv6, you have to use IPv6. If it has both, you can use whatever you want. There's an official internet document that says in such a case, in most cases, you should prefer IPv6 because that's the current thing. Why do the old if the new is available? But many systems have found that IPv6 very often does not work well. We will talk about that a bit later. Reasons for IPv6 not to work very well is that many systems, that's the case of the www.epfl.ch, which is entirely programmed in, it's an IPv4 system. But in order to still work if IPv6 works, we do a proxy of this server that first gets the message and then repeats it to the true website. So if you use IPv6 to communicate with this, you always have larger latency. You go through an intermediate system that is at the application layer. So it's probably much slower than going directly there. So that happens a lot. And some systems are providing system services to allow an application to know which of the two it should use, not just go to DNS, but also ask the operating system what are the statistics, for example, in terms of latency of using one or the other. So in my experience, Macintoshes do it, and my Windows machine does not. If I use IPv6 on my Windows machine, I'm always very slow. So I practically disable it, but on Macintosh, in my experience, it doesn't happen. This slide is important to give you the mental model of UDP. Beyond the programming things that you will need to learn to do the programming lab, when you reason about how things are, it's good to have a model of what is happening below the hood. So this is a very superficial explanation, but that's one that I believe is true. The operating system, when you create a socket, you can think of a socket as a buffer. So whenever you create a socket, you create a message buffer. Why do you need a buffer? Well, you need a buffer when you send, because when the application writes, you need to put the write somewhere. It's not instantly sent on the wire, so you need to, and more important is on the receiving side. When a message is received, The application may read it or may not read it, depending on the when it executes and which step it is executing. So it's used for sending and for receiving. Here I'm showing IPv6 and IPv4. So this host has this IPv4 address, that IPv6 address. The first thing that we see here is that the IPv6 world and the IPv4 world are separate. So you can have a machine that listens to a given port number on IPv6 and another port on the same port number on IPv4, and those can be two different behaviors. You should have seen that with TCP, but the same applies to TCP and UDP. When we, in the first lab, we asked you to go to lca.tpfl.ch, and if you went through IPv4 or IPv6, a little thing was different. With IPv6, the web page showed an IPv6 logo. That means the program knows whether it's getting from one or the other. And one way to make it know, one extreme way is to have two different programs that respond to the two different sockets, because IPv4 and IPv6 are two different worlds here. A socket, a UDP socket, is essentially, if it's not connected, associated with a local address and a local port. By default, that's the behavior. So a socket means an ID that is given by an IP address and a local port number for a UDP standard socket. For a UDP connected socket, it is both port number and addresses on this system and on the remote system, the association of both here. Unanimity for A. So if the packet is lost, in that case, for UDP, it's very easy because the logic of the application requires a response. So you don't need to have an acknowledgement like we would have in other systems. You ask for something. If no response comes, you conclude that something went wrong and you ask again. This is what the DNS client will do, and this is a prototype use of UDP. This is really what UDP was made for this kind of very simple interaction, where the logic of the application does not require full reliability because you will repair things at the application level. If you are not happy with that, then the standard today, in many cases, not all, as we will see a bit later, is to use TCP. TCP is taking care of packet losses. Why are packets lost? Well, a very standard case is transmission errors on wireless systems, for example, so physical layer errors. When we will talk about congestion control, we will see that, unfortunately, in the internet, there are also many packet losses due to buffer overflow. The internet is a very large queuing system. When packets go into a bridge or a queuing or a router buffer somewhere on the output of a line, for example, you need to have queues. Why do you need to have queues? Well, if you have a router that has 100 ports, and for some reason at one point in time, and all the ports at, say, 1 gigabit per second, say during a short period of time, all ports, all 99 ports, are sending traffic to the same output port. Then you have traffic that comes in at 99 gigabit per second over an output link of 1 gigabit per second. So it will be impossible in a case like this to serve all the packets as they arrive. So you will need to put them in a queuing system. It's not always the case. If you have 99 ports at 1 megabit per second and an output port at 1 gigabit per second, there will not be a problem. But this is not the typical case. Typical case are the speeds of the lines, at least in the backbones, are the same in all directions. And then traffic goes, we don't really control exactly where traffic goes. So we need queues. Managing queues will be the topic of the congestion control chapter that we'll see next. But the side effect of that is once in a while, and sometimes frequently, we may drop packets because of queues that are full. And we'll see making queues very, very large is not a solution. So we will need to drop packet once in a while. And as we've seen, TCP solves the problem for the programmer. What does it do? Well, it solves the problem, but in order to do that, it imposes a restriction that we've mentioned already. TCP guarantees or offers what we call a streaming service, which means that it guarantees that packets are delivered in sequence. It's an added value if you want, but as we will see, that also might be a drawback. So the initial idea, this was done in the 70s, was to make over a network the equivalent of what we have over a physical line. If you connect two PCs with an Ethernet cable, then packets may be lost on the cable, very, very rarely if you do that, but once in a while it might happen. But what can never happen is that packet 2 that was sent after packet 1 arrives before packet 1, if you connect them by a line, because a serial line is preserving sequence by the way it operates physically. And TCP is emulating this. So TCP guarantees that if I send you 1,000 packets, they will arrive in exactly the order in which I have received, in which you have sent them. It does not exactly do what I just said. It will not deliver packets. It will deliver the data in the order in which it was sent. The difference between packet and data is that TCP completely reshuffles, does not have the concept of packets when it delivers messages to the application layer. In fact, TCP does not deliver messages to the application layer. TCP puts things in a buffer, and reading from a TCP socket is like reading from a file. You read bytes or blocks or whatever you want, but there is no concept of one block is being received or not. In order to do its job, TCP numbers everything, and because it's offering a byte-based service, it numbers everything byte per byte. This is why the TCP numbers are a bit clumsy, and when I illustrate some of the things in those slides, sometimes I will put packet numbers because they are much shorter, but the real thing in TCP is that everything is numbered in bytes. And then whenever TCP sends some data, it requires acknowledgements, and if acknowledgements are missing, TCP will retransmit. We've seen an example of that. We called it the stop-and-go protocol. I send packet from A to B. If packet is lost, I require an acknowledgement. If no acknowledgement comes after a timeout, I retransmit. But we have seen that this protocol has bad performance when the bandwidth delay product is small. This is what TCP is addressing. It will be a bit smarter than the stop-and-go protocol. This is our first approach to the TCP, to the operation of TCP. I'm showing a space-time diagram. Time goes vertically, flows vertically. I have A on the left, which is in that case a sender. B is a receiver, and A is sending data. So a first packet is sent. Inside the TCP packet, in the TCP header, there is what is called sequence numbers. So here it's 8001 to 8501. The convention in most TCP traces is that the numbers that are shown are the next ones. So this means this is the first byte number in the packet, and this is not the last, this is the last plus one. So the byte numbers in this packet are 8001 to 8500. So this, if you want, is the next expected byte. But the nice thing is you just do the difference and you have the packet length. You don't need to do plus one. This packet is received. The job of B is to send an acknowledgement. So TCP will send an acknowledgement here. As we will see, acknowledgements are simply TCP packets that have no data. Or if B would have something to send back to A, it could send the acknowledgement in the data that is sending back on the reverse direction. But here I'm showing only one flow. Data is flowing only from A to B. We will see the complete picture a bit later. So here, this acknowledgement is coming, and the convention for acknowledgement is we're acknowledging the last byte plus one. So this means this packet has been received. Then packet 3, 4, 5 are sent, one after the other, and it turns out that packets, those first two packets of the sequence are lost here. The third one is received. What B will do when receiving it, it will send an acknowledgement because there is always an acknowledgement to send, and the semantic of the acknowledgement field is that we always acknowledge the largest number that has been received in sequence. So here, things have been received in sequence up to this number, 8500 plus 1 gives 8500 1. I have received some other information, but it's not in sequence. There is a gap. Those two blocks are missing. So I acknowledge this number, not this one here. We will see that we will do something else called a SAC block in a minute, but the acknowledgement field does not contain this. Now, hopefully, sooner or later, the source will detect that something went wrong. There are many possible mechanisms in TCP. Here I'm showing one simple one, which is a timer. When packet 3 was sent, the timer was started. That hopefully is larger than the round-trip time. And then when it expires, this sender knows that this packet is lost, and like in the stop-and-go protocol, will retransmit it. Here I'm showing a very basic behavior of TCP, which is valid, is allowed. It is transmitting only the packet that it thinks is missing. It thinks packet 3 is missing, so it retransmits it. Now, when it's retransmitted, now the bytes that have been received in sequence are all the bytes still up to the bytes up to 9,000 here. So those bytes can be delivered to the application, and we will ACK again this number 9001. The following block here that has been received is not ACKed in this figure here. So this is how the ACK and sequence number field work. And this is how things were at the origin. But of course, as you can see, this is not very intelligent, because here, when we are ACKing this number, we're not giving the information that we have received that last one. So when we receive 7, we don't, so here I'm assuming it has been received. In the previous slide, it was lost. Here I'm assuming it's received. If we just give the ACK, A doesn't know that this thing has been received, so it might retransmit it unnecessarily. So what we do in TCP is we indicate in what is called selective acknowledgement, SAC blocks, we indicate the blocks of numbers that have been received. Here, the blocks that correspond to this packet are indicated. So at this point, A knows several things. It knows, because there is a gap here, it knows this is the sequence number field, and the SAC, it knows something has been received, but also something is missing. So A can decide now. It's a hard word to decide. A, in this case, could decide, oh, I've sent packet 3, 4, 5. I receive an acknowledgement only for packet 5. I can conclude that 3 and 4 have been lost, and I retransmit them. This is what A is doing. It is retransmitting them in this case, because it concluded it was a good idea. As we'll see, TCP has a lot of flexibility. The flexibility is the price to pay to the fundamental impossibility of distributed systems. A TCP source cannot know exactly what has happened and what the destination knows. Because in order to speak to the destination, you need to use TCP. We don't have an out-of-band channel like we have here. We see everything on the picture, but A sees only what it receives. It doesn't know whether the packet is lost or whether the packet was simply misordered and will arrive a bit later, or whether it's the acknowledgement that was lost, like in the previous case. Here it receives that. So here it guessed and decided to retransmit. When we see is that when it retransmits here, it has retransmitted 2 packets together. This is possible. It is possible that TCP here is sending packets of 500 bytes because this is the speed at which the application is generating the bytes. The application program might be slow, or it's a real-time application that does not need more speed than this. So it's generating blocks of 500 packets every so-and-so, and TCP sends them as soon as it can. Now, if it has to retransmit, and if the maximum packet size is 1,500 bytes, then TCP can put up to 3 packets in wide. So instead of retransmitting 2 packets, it will retransmit only 1. There's only benefit in terms of utilization of the CPU, in terms of utilization of the bandwidth of the line, because there's only 1 IP header and only 1 TCP header. And it's allowed because TCP offers a streaming service. TCP does not guarantee that the packet you received are exactly as they were sent. So this is what is meant here when we see UDP is message-oriented, TCP is not. When I receive those bytes in B, I don't know whether the application has written them as 1 block or 2 blocks. In that case, it was written probably as 2 blocks. We don't really know in this diagram what the application did. We just know what TCP did. But if TCP did it this way because the application took some time to create the different blocks, here the repetition does not. Now, when the B receives this, the loss is repaired, so it can deliver all the bytes that have been received, the two missing one and this one, that had been received but was not made available to the application, but was kept, of course, in the buffer. Now it's made available to the application, and the next ACK will ACK the largest part here, which is now no longer missing. So this is the standard way, the most frequent way of that TCP operates. Now, what happens on the destination side? We need a buffer here. We need a buffer for several reasons, but the primary reason is when data is received out of sequence. This is the example of the packet 5 here. It is received and it's out of sequence. Now, a stupid implementation of TCP, it would be a valid implementation, but not very efficient, would consist in dropping it. You say, oh, you're out of sequence, get out of my way, I have not received it. But of course, we don't want to do that. You keep it in a buffer, because very likely what will happen is the missing segments will come very soon. So it's put in the buffer, so there is a receive buffer. So this is illustrating 3 different snapshots of the receive buffer. That's a buffer that's in the socket, in the TCP socket that's using that. So when this packet is arrived, it's put in the buffer, and it's available for the application. When packet number 5 arrives, it's put in gray here, it's put in the buffer, but it's not available to the application. If you write a program that does a read from this socket, and it will be able to read the first packet, but not this one, because it's out of sequence. When the loss is repaired, which occurs here, then the entire block here is available. And here I'm assuming the application is lazy, has not done any read. So during all this time, the application has not consumed the data out of the buffer. So the data is still in the buffer. Now, it's not sufficient to do everything we said here. We need what is called in TCP a sliding window. So what is a sliding window? First, why is it invented? Well, the first reason to invent it was to avoid overflow of the buffer. This is showing a pathological example, but that may arise. Pathological examples are rare, but if you run a server, this program will run for months without rebooting, hopefully. And if a pathological case occurs once every 1 million cases over a month, it will happen. So if it happens, bad things like this one could happen. A bad thing here is that a packet is, by bad luck, is discarded several times, is lost several times on the line. Packet P0 is sent, is lost, and it's not ACKed, of course, but if there is no mechanism to stop the sender from continuing sending, so here the sender continues to send, P1, P2, P1000, and P0, it tries once in a while to retransmit it, but bad luck, it's always lost. Then what will happen on the receiver side? The receiver side that offers the streaming service will buffer everything. So it will buffer packets and packets and packets, and if that happens, once, probably nothing bad will happen, but if it happens several times in your server, you will start having memory problems and your server might crash at some point. So we need a way to prevent the source from sending without limit. And this way is called the sliding window. Here I'm showing an example of a sliding window. A sliding window is a given volume of data. Here it's counted in bytes, 4,000 bytes. We will see who decides what that value is in a minute. Assuming here it's 4,000 bytes and all packets are 1,000 bytes, so it's 4 packets, essentially. I'm saying packets here to make this cartoon short and simple, easy to understand, but in reality, as we have seen, TCP has a lot of flexibility and can decide to count in bytes. The window is 4 packets, and I'm assuming the source has all those packets to send. So what it can do is can send 0, 1, 2, 3, 4, because the rule of the sliding window is you are allowed to send the packets that are in the sliding window. So it will send 0, 1, 2, 3, 4, Another question is, how does the window slide? It's a sliding window, so it moves. And it slides when packets are acknowledged in sequence. So the lowest edge of the window, the left part, must be such that all the packets before it have been acknowledged. So when packet 0 is acknowledged, which occurs here, then we can move the window, and now we're allowed to send packet 1, 2, 3, 4, which we do. We send packet 1, 2, 3, 4. We receive acknowledgement for packet 1, so we can move the window, so we have 0, 1. But packets number 2, 3 have been sent but not acknowledged. So in that case, you have to wait. You have sent them already. You can resend them if you want, if you estimate that you have indication that they were lost. But you cannot send packet 6, for example, even though you could say a window of 4, but no, the window is blocked at the non-acknowledged packets. And in the worst case, if no acknowledgement is coming, you have sent all packets in the window. That means the sender is blocked, cannot send anymore, which is the desired behavior. This is a case where the receiver has not acknowledged anything, so the receiver has stored the 4 packets probably and is full, and the receiver estimates that 4 is enough and wants you to not send more. It's exercising back pressure or flow control on the sender here. Sooner or later, hopefully, the acknowledgements are received. So when acknowledgement 2 is received, the window moves to 3, and we see here a case where acknowledgements are received one by one. The window moves one by one, and whenever we receive one acknowledgement, we can send one packet here. So we see that this sliding window has the effect of pacing the rate at which the source is sending to the rate at which acknowledgements are sent by the destination. So if the destination, for whatever reason, is not sending them, the source will need to stop, which will protect the destination from overflow. Now to the quiz that I wanted to show you a minute ago. And the correct answer is the majority, is B. B is the correct answer. The window is 4, and the only acknowledgement is -1. That means 0, 1, 2, 3 have not been acknowledged. So the only thing we can send is 0, 1, 2, 3. So packet 4 cannot be sent. Even though the sender knows that packets 1 and 2 and even 1 and 3 have been received. So the selective acknowledgements are useful to prevent the sender from retransmitting things that have been sent, and perhaps for other things, as we will see a bit later. But it's not used for moving the window. The window is really contiguous things, and everything before the window must have been acknowledged here. We see also that in the receiving side, we must buffer everything here. Packet 0 has not been received. Because of that, we must buffer 1, 2, 3. And because the receiver does not want to buffer more, this is why this window size is imposed here. However, so a window is necessary to prevent overflow of the receiver, but is not sufficient. Here's another example where the problem is that the application is slow for reading on the server side, typically. So you send, or on the consumer side, you send data from A to B, and everything is nicely acknowledged. So the window moves, but for some reason, the application is not reading it. You can tell me this is pathological, but no, this is not pathological. This is the normal case. So when you write programs, you have to imagine things will be in this way. When you send data from machine A to machine B, you have no idea what happens on machine B. Is machine B consuming them at the speed that you send them on A? You don't know in general. You should not assume that things will work well. You send at any rate from A, and you assume that B will receive it. If you do that, it won't work. I mean, people in the smart grid who do PMU streaming, where some sensors send data using UDP to an application that receives it, they make that bitter experience that if you don't control the number of PMUs, how fast the server is, etc., you lose data if the server is not fast enough to receive them. It can be the server, it can be the client, it can be a server that's sending a lot of data to your application, but your application is, I mean, you have an iPhone or a smartphone of any kind, and it's busy with the operating system doing whatever in the GUI or whatever. So you don't know at what speed an application program is reading application. Here, lots of data has been received. They've been properly acknowledged, so everything is fine from the server, but they are here in the socket buffer. Now, socket buffer are in the operating system space. The operating system space is not very large, so you don't want this to happen. If that happens a lot, your machine will have problems. You will have memory problems. So you need to do something. That something is called flow control. That's exactly what flow control means. Flow control in general means adapting the rate at which a source is sending so that the receiver, the destination, can consume the data without being congested. That's called flow control. Do not confuse with something that is very close, which is called congestion control. Congestion control is very similar. It is adapting the rate at which a source is sending, but the goal here is to protect the network, not the destination, protect the network. So congestion control in the context of the internet means protecting the network from buffer overflows. Remember the queuing systems I mentioned a few minutes ago. If you have your 1,000 input ports that are going to the same output ports, you must somehow signal to all the sources that are sending to the same output port that there is congestion. They cannot send at this rate. You cannot have 1 million sources that are sending to the same output ports. They have to slow down. That slowing down is called congestion control. It's also done by TCP, typically, but we'll talk about it later. Right now, we just talk of flow control. So how is it done? Well, simply, something very simple. We adjust the size of the window. Let me show an example here. Let me show the same example as before, but now the destination is manipulating the size of the window. There is a field in TCP header, which is called window, and it is a field, it's like the acknowledgement. It concerns the return channel, and it means what is the size of the window that can be used by the other end. So here, the right part is signaling your window now is 2. So you can send 0, 1. We send packet 0. Then we receive an acknowledgement saying the window is 2, so we move, we can send 1, 2. For some reason that we will explain in a minute, the receiver can now decide, oh, the window is larger. So then the source can now send 1, 2, 3, 4. And we see that the destination here can manipulate the window. In the worst case, it can send a window of 0. So if you receive a window of 0, that means you block the source here. So this is what the sender should do in the previous example when we had the receiver should do in the previous example where we had a receiver that is flooded by a very fast sender. At some point, it will send a window of 0. Window of 0 means we stop the sender. There's no point sending me 1 million packets. I'm still busy processing the 500,000 previous ones. So you might as well stop. TCP allows that. TCP will do that automatically. You don't have to program anything to do it. If TCP is not able to receive, it will do the congestion, the window equal to 1. Oh, sorry, not congestion. The window field will be equal to 1. Of course, it's very dangerous to do something like this. If you send a window equal to 0, what is the danger? Someone can attack you, yes. That can be done, and we have no protection against that. If you can sneak into that TCP connection, we will see that we need a number of things to get into a TCP connection. But there's something more trivial, that doesn't even need an attack. Although an attack can help making the case where. If I send you a stop signal, right? I expect that sooner or later I will remove that stop signal, so which is done here. I had a window of 0 followed by a window of 4, but everything can be lost. So what happens if this message is lost? The next message is lost, right? So this one is blocked. So it thinks the destination is busy or has hung out, the process has crashed or whatever. So things don't work. I don't see any point in continuing to send. This one believes that the source has nothing to send because nothing is coming back, so both will remain silent. Right. So you have what is called a deadlock. A doesn't send because it believes B is not ready to receive, and B receives nothing because it believes that A has nothing to send. Right? So you need mechanisms to break such deadlocks. So in TCP, a mechanism is when you receive a window equal to 0, a timeout occurs. When you receive a window equal to 0, after some timeout, you will still send 1 byte of information, 1 byte. So you're allowed to send 1 byte. And if the thing is really blocked, then this byte might be dropped, but okay, you've lost 1 byte, no big deal. But if it was due to the deadlock, then the deadlock will be broken, because then the receiver will receive that byte and will repeat the previous message, which was a window of 4, and then you've broken the deadlock. Here is below the hood why the system on the right has sent those windows. I'm revealing here the state of the receive buffer, of the socket buffer here. In dark blue is the packets that have been ACKed, but have not been consumed by the application. So here, -2, -1 are ready. The application does a read of 1 packet, for example, and here it does another read and reads everything. And we see that the window size is updated as a function of what has changed. Here the socket buffer is 4 packets, and 2 are occupied by packets that have not been consumed by the application. So I'm signaling to the source, you can send 2 more. I have space for 2 more in my buffer. Here, when the application has read everything, I signal to the source, now you can send 4 more. And I signal 0 when the buffer is full. So I've received everything, but the application has not read yet. So I send a window of 0. Now, a millisecond later, the application reads everything. When that happens, I can send a new acknowledgement with no data, just an acknowledgement, and a change of window, and that will unlock my peer system here. Voilà, we do a 15-minute break.